Hello, everyone. Today we introduce the notion of an orthogonal matrix, which is a slightly delicate definition, but we'll see that it's very important for the last few sections of this class. So here's the definition. A matrix, we say it's orthogonal if its columns are an orthonormal basis of Rn. And I should emphasize that this is a quirk in the linear algebra terminology. It's not enough that the columns are orthogonal, they must be orthonormal for the matrix to be orthogonal. They're very important. We'll see some examples. For today, we'll just see some very key properties and a slight example, and then starting next time, we'll use them until the end of the class. Okay, here's some basic examples. If I take the identity matrix in any dimension, really not just in dimension 3, this is an orthogonal matrix because its vectors are all unit vectors and they're all orthogonal to each other. In other words, the standard basis E1, E2, E3 is an orthonormal basis. Something a little bit more interesting is a matrix like this Q matrix here. In fact, its columns A1, A2, and A3 are an orthonormal basis for R3. To do that, one should check that all of these columns are unit vectors. Let's check it with 1. Let's take A1. Well, the norm of A1 is the sum of the squares of its entries over the square root. So it's 1/2 plus 1/2 plus 0, but that's square root of 1, which is equal to 1, which is good. If you take the dot product between, for example, A1 and A2, you get 1 over root 2, comma 1 over root 2, comma 0, dotted with 0, 0, 1, and that just gives you 0. Let's not, I won't do the other checks, but they're all simple like these. And I encourage you to try and check everything about this matrix. An example that we've already seen, but we never considered it as an orthogonal matrix, is the rotation matrix. By definition, the rotation by an angle theta is cosine theta, sine theta, minus sine theta, cosine theta. These two columns are unit vectors. If you are geometrically oriented, you may remember that the vector cosine theta, sine theta is a point on the unit circle, so its norm is 1. And you can think about it in the same way, and by rotating that point by 90 degrees, you get the point minus sine theta, cosine theta, which is also a point on the unit circle. If you like algebra a little bit more, you'll notice that in both cases, both for T1 and T2, the norm of these vectors is given by the sum of the squares of their entries, which in both cases is given by cosine squared plus sine squared, which is equal to 1 by an algebraic identity, by the Pythagorean identity. So we're taking the square root of 1, which is 1. And then it's not hard to see that if I dot these two columns together, I get 0. Let's try to do that. If I do the dot product between the two, I get minus cosine theta, sine theta from the first entries, plus cosine theta, sine theta from the second. And so these two cancel and you get 0. That's an important example. The power of the notion of orthogonal matrices is in this alternative definition here. You can define a matrix to be orthogonal by requiring that Q transpose times Q is equal to the identity. So, and that's exactly equivalent to saying that its columns are an orthonormal basis. So let's try to convince ourselves why it's equivalent to say that a matrix is orthogonal, so its columns are orthonormal, and Q transpose times Q is equal to the identity. Well, the way to convince you of that is, let's just write down Q, writing down its columns. I'll do it for a 3 by 3, but the argument is the same in general. Then if you take Q transpose times Q, you can write it like this, where these two are 3 by 3 matrices, and now I'm when I write Q, I mean that V1, V2, and V3 are 3 column vectors. And when I write Q transpose, V1 is a row vector, V2 is a row vector, and V3 is a row vector. When you multiply this together, you get a 3 by 3 out of it. But by the matrix product, the first entry up here will be given exactly by the dot product of the first row times the first column, which is v1 dot v1. When you compute the second entry here, you'll be dotting v1, the first row of the first matrix, with the second column of the second matrix. So you get v1, v2, dot v2. The third will be v1 dot v3, and so on for all the others. When you compute a matrix product, you're always dotting one row of the first matrix with one column of the second. So you get this product here. Now, saying that Q is orthogonal is the same as saying that vi dot vi is equal to 1 and vi dot vj is equal to 0 for I different from j. So, oops, it's written there. So I repeated myself accidentally. Q is orthogonal means that its columns are orthonormal, which means exactly those two conditions here. But then if you take these conditions and you plug them into this matrix that we computed up here, you'll see that you get ones on the main diagonal and then zeros everywhere else. In other words, if these two conditions are true, then Q transpose Q is indeed equal to the identity. And the converse holds as well. If Q transpose Q is the identity matrix from here, from this matrix up above here, you can see that, well, the only way that that can be true is that v1 dot v1 is equal to v2 dot v2 and v3 dot v3, and they're all ones, and all the rest is zeros. So the argument goes both ways. In other words, Q is an orthogonal matrix if and only if Q transpose Q is the identity. And this is important because it has very crucial consequences. For example, one thing that we learn immediately is that if Q is orthogonal, then Q transpose is also orthogonal. Because if Q is orthogonal, then Q transpose times Q is equal to the identity. But I can transpose both of these, and I mean, this also shows that Q transpose is the identity. By transposing everything here, I get that Q transpose Q, all transpose is the identity transpose, which sounds like a tongue twister, but this is actually yeah, I guess it did twist my tongue. I'm going nowhere with this. This implies that Q times Q transpose also is the identity. Because, let me think about it. Let's not do a proof of this fact. It's not obvious, but it follows from this consequence that if a matrix is orthogonal, then so is its transpose. Essentially, so the idea is that you can write Q transpose Q can be written in terms of rows. Instead of columns. So the proof would be the same as the proof that we just did to show that orthogonality implies that Q transpose Q is the identity, but you can tweak the argument and say that it also works for rows. An important consequence of this is that since Q transpose is orthogonal, then the rows of Q are also an orthonormal basis because they are the columns of Q transpose. Let's have a look at some other properties. The determinant of an orthogonal matrix can only be plus or minus 1. The reason of this is that if we have Q transpose Q is equal to the identity, that implies that the determinant of Q transpose times the determinant of Q is equal to the determinant of the identity, which is 1. But the determinant doesn't change when you transpose a matrix. So this is equal to the determinant of Q squared. The determinant of Q squared is equal to 1 means that the determinant of Q can only be plus or minus 1. The inverse of an orthogonal matrix is its transpose. That's very simple because writing this means exactly that Q transpose is acting as the inverse of Q. This is one last property, which is last but not least, it's also very important. The matrix Q preserves dot products. So if I apply the matrix Q to a couple of vectors U and V, and then I dot them together, I get the same result as I would have gotten by dotting U with V without applying Q. The reason why this is true is a fact that we mentioned a while back about dot products. I can essentially, in a dot product, I can move matrices across, but I have to transpose. So if we apply that with the quantity that we're interested in, this is equal to U dot Q transpose QV. But Q transpose Q is the identity matrix. So this is equal to U dot V. And as a consequence of this, orthogonal matrices preserve length of vectors. That's what's written here. The length of QU is equal to the length of U. And this is an immediate application of what's above because QU squared is equal to QU dot QU, but by property 4, this is the same as U dot U, and U dot U is the same as norm of U squared. So you can take the square root, and these are positive numbers, so the property is satisfied. Okay, let me finish by mentioning one important example of orthogonal matrices. We actually know what all possible orthogonal matrices are if their size is 2 by 2. So in the 2 by 2 case, orthogonal matrices are classified. And they're classified as follows. If the determinant of an orthogonal 2 by 2 matrix is 1, we've already seen this, Q can only be a rotation matrix. If instead the determinant is -1, and remember that these are the only two possible cases because the determinant of an orthogonal matrix can only be 1 or -1. Q is what is called the reflection matrix. It's denoted as theta, and it works like this. You have a line whose angle formed with the x-axis is theta. I use the term, like, to be precise, one can say that the slope of the line is the tangent of theta, but this is what it means, that the angle of the line with the x-axis is theta, and you reflect across it. So if you pick any point here, it will just get sent across by our matrix as theta. It looks like this. It's another example that I decided not to focus on as much as rotations, but it's equally important. And they are all the orthogonal matrices of determinant -1. This classification here seems pretty harmless, but it has one very surprising consequence. Let's see. there's something that we already know. If I take two rotation and I multiply them together, I get another rotation of the sum of the angles. So far, so good. If I do two reflections across two different axes, two different lines, the composition of them, so reflecting once and then reflecting another time, is the same as doing one rotation. And the reason why that's true is just because of determinants. Suppose I have my two reflections. I'll take two angles as gamma and delta. So I'll do the reflections like this. When I take the determinant of S gamma as delta, that's going to be the determinant of S gamma, reflection 1, times the determinant of S delta, which is the reflection 2. But this is -1 times -1. So the determinant of this product is equal to 1. In other words, the product of two reflections must be a rotation of some other angle theta. One could compute the relation between gamma, delta, and theta, but that's beyond the scope of this class. The important thing here, and I think it's very surprising, is that you can show without drawing a picture that doing two reflections must actually be equal to a rotation. I do, however, encourage you to try and draw a picture in which you take two axes of reflection and reflect a vector across each of them and see that you're actually rotating things around.